Okay, so I think we've got a few more people that have just joined, so I think we'll just make a start now. So I'm Dr. Kulvinder Panesar, an assistant professor in applied AI from the School of Engineering, AI and Electronics. So I'll be your host for the next hour for this amazing and thought-provoking talk on trustworthy artificial intelligence comes with real understanding of language. Now, we've had a great interest in this talk, and it's quite an apt talk for everybody who's using AI, and that is a lot of people. Yeah. So our fantastic speakers, John, Ball, and Beth, whom I've known for several years. We have a common interest in role and reference grammar, and they're from Sydney, Australia. So it's great to be able to see how research has moved, how there's been a fusion in research across linguistics and computer science and AI as well. So the talk will be about 30 to 40 minutes, followed by a Q&A. Well, enough of me. Let me introduce our speakers. So John Ball is a cognitive scientist, author, and entrepreneur. And he he's been, since his computer science undergraduate days, he's been absolutely fascinated with how the brain works. And today in his talk, he'll show the result of his brain science work in emulating language understanding for machines. So over to you, John and Beth. The floor is yours, and thank you coming from all the way from Sydney, Australia to do this talk. So over to you, John. Thank you.
Thank you very much, Kulvinder. Can you guys hear me okay at the back? Yeah, great. So it's worth traveling 10,000 kilometers to actually talk to you guys today. The purpose of the agenda is just to introduce a couple of scientific breakthroughs, so different ways of thinking about AI that you can potentially apply or potentially access through the system that I'll demonstrate to you. From my perspective, the overview of this talk, if you remember nothing else, is that I'm talking about unsustainable AI. We have AI today that's taking up the world's energy use, and there's a different way of doing it. The solution comes from brain science, which from about 1980 until 2000, I was working on very seriously, reading everything I could on brain science. And then from 2000 until the present, I've been building a system that can demonstrate how we can use brain science with linguistics in order to produce AI. So here's the key automation slide. We have an AI breakthrough, and the next generation of AI is going to be based on cognitive science, and the thing that we can call that is cognitive AI. Generative AI is in crisis. Why is it in crisis? Well, because the leaders of generative AI have been telling us that we've got super intelligent machines that are going to replace all of our jobs. They're going to handle robotics and everything that we could possibly imagine with AI. But it's not working, and the reason is because it's not the right system to do that. Cognitive science introduces the solution, which is brain science. So my Patom theory that I developed, as I said, by 2000, and a thing called role and reference grammar that I'll explain more in a moment. Basically, role and reference grammar looked at the world's diverse languages and came up with a model that worked for everything. I don't know if you guys heard of Galileo, scientist. So what Galileo did was he took studying astronomy to a different level by simply building telescopes and observing what was happening in the skies. And he could see planets with their own moons around them, and he kept building on the science by making observations. That's natural science, but formal science is a different one, like mathematics, where you just make your own rules and then you can keep manipulating your own rules. And the challenge with formal science is you can't falsify it. I can simply say, well, I'll just change the rules and now it'll work. And what we've seen in the generative AI space is people saying we only need 1 or 2 breakthroughs in order to solve these problems. And the trouble with breakthroughs is they might come through every generation or two. They don't come through just because you put a lot of people on a project to solve a problem. So cognitive AI is probably the right term to use going forward for the next generation of AI. In terms of linguistics improvements, We've had about 70 years of linguistics with maybe longer, maybe since Bloomfield in 1933. The idea was that linguistics can be managed without referring to what the brain is doing. So you can do this with the behaviorist model. And that's been pursued since about 1933. But that model's too simple. And if you have a scientific model and it's too simple, it's not the right model. As Albert Einstein once said, make a scientific model as simple as possible, but not simpler. And a missing piece is meaning and context in linguistics. So when you see a word, you convert it to meaning, and then the meaning is manipulated with the rest of the sentences. And a key element is this idea of common ground. So we're in this meeting room now. The people here can see me, and so the common ground is really this immediate situation. So we call that immediate common ground. But equally, there's general common ground or background knowledge, and that's all the information we know about the world up to this point. In order to use background knowledge or general common ground, we still have to share that experience. And there's some rules that bring that make it active in the immediate common ground. One of the points that I would often make is that if you have a knowledge repository with Patom theory, and then you say, I want to have all of the patterns that relate to some element of it, I call that intersection. You're simply taking all of the possible patterns stored in a brain, and by determining what the elements are that you care about, you basically cut through the knowledge representation and extract what you require. So last bit is that the biggest change in linguistics needs to be conversion from parts of speech into semantics. So rather than syntax, if we use semantics, we can now do lots of things like generalization that you can't do if you're simply looking at words or parts of speech. Semantics is better with predicates and reference. And to give you an idea how the two work together, if you say the party is tomorrow, it makes good sense in English. If you say the man is tomorrow, it makes no sense because a referent, a man, is something that doesn't have a temporal dimension, whereas a party has a start time and an end time, and as a result of that, you can talk about when the party starts, tomorrow. And vice versa, the man is happy, that makes sense in English, but the party is happy doesn't make sense because a party is an event and events don't have feelings like happiness. And this is coming back to an illustration of the fact that predicates determine their arguments. So in the case of tomorrow, tomorrow allows party, but tomorrow doesn't allow man. Happy allows man, but happy doesn't allow party. And by using this combination of elements, we're able to reduce the number of combinatorial possibilities that we even need to consider. It's a completely different way that solves a lot of the problems of the combinatorial explosion that took place from the 60s to the 90s with the rules-based systems. Let me talk about the AI crisis in a bit more detail, because not everybody accepts that we're in an AI crisis. Is AI solved? Anybody think AI is completely solved now? Right. So some of the things that need to be solved is, if you walk into a bank and you say, can you transfer to the robot that meets you, can you transfer $100 into my checking account? There's no robot that can do that. It doesn't understand what you're saying. I think Amazon spent like $15 billion to make Alexa work so that you can order everything by voice. So that's what people are working on. Robotics, self-driving cars. By 2020, nobody needs a car because it's all been solved, according to Elon Musk. Speech, if you've seen captioning, there's errors in the captioning. So it's pretty good, but could be better. And is the information that we store lossy or lossless? So if you took a book and you stored it in an LLM, can you extract everything from every book that's in there? And you can't. So for that reason, statistical AI is in crisis. And a scientific crisis becomes a proper crisis once the people that are controlling it can't work out a solution, can't work out a way forward. And we're pretty much hitting that point. In Australia at the moment, we've been talking to the government about this one particular topic, unsustainable AI. So in the US in particular, but in Asia in particular, people are building data centers. The governments are putting billions and billions of dollars into building data centers with extra power, with water cooling, in order to drive these new generative AI data centers. And it's there's a better solution. Instead of spending billions of dollars on this technology that has these other problems like hallucinations, errors, IP theft, the cost $100 million to build a large language model or more, and the bias that comes in where the people that control the systems get to decide what the answers are going to be to certain topics. You know, maybe in the future you can never say Donald Trump's not a good guy, but you can say Donald Trump is a good guy. One, it'll agree with you, the other will say I don't have an opinion. And you don't really want foreigners you don't want people to control that type of thing. You can probably not see that at all, but these are the top 37 companies in market capitalization today. The point I wanted to make is that these red ones are unsustainable. These are the energy companies. So there's Saudi, Chevron, Exxon. All of these other ones are technology companies. So you'll notice NVIDIA at the top, $4 trillion US capitalization, Microsoft, Apple, Alphabet, Google, Amazon, Meta. So all of the biggest companies in the world are getting these huge market shares because of generative AI. They're all pushing to start to build data centers which are unsustainable, and all the governments are falling into line behind them because the governments want to be part of this. Don't miss out, that's the catch cry. So all of these things in my book, which is this, I wrote this last year, How to Solve AI with Our Brain, the Final Frontier in Science. The idea was to take what I was doing when I was 5 years old, watching Star Trek, thinking, I need to solve this problem. I want to be able to talk to a computer and have it respond to me. It takes the ideas of the computational model that I've been taught all my life and then looked at how can I make that work. And you'll see the conclusions. You can't make it work as a computer, or not easily. And it comes back to this problem here. Hans Moravec, Marvin Minsky, in my book I talk about in the 1980s, I contacted him and I said, I want to solve AI and I've got this great idea with brain science, how can I do it? And he said, look, there's two things you have to do. The first thing is you have to have a working prototype. And I thought, oh, that's going to be hard because, you know, it's like the moon mission. And the other thing you have to do is write it. And then I thought, well, this book writes about it. But what I hadn't realized was with the work I did to do the engineering, you have to actually be able to talk the other people's language. And so when I was talking to academics, they were saying, I don't know what you're talking about. And Terry Winograd, he's the guy that did the block worlds model in 1970, 1980. That model, he said to me, look, I know what you're saying, I know what you mean, but nobody else will, so get your science right. So you need the science and then you need the demo, because as Minsky said, lots of people have good ideas, but they don't work in practice. I've just got one example here. So this is a 1980s paradox, which is things that are easy for computers, like memorizing the phone book, are hard for people, and things that are easy for people, like mimicking words that other people say, are hard for computers. And so that copying speech sound that we use as children is difficult. So what is it that we can change? Tom Dietrich put it pretty well. He went around the US in 2023 talking to universities about the limitations of large language models. And there's a few key points that he makes that we should be paying attention to. Of the flaws, he points out the statistical models of knowledge bases, not knowledge bases. So when a language model hallucinates or confabulates or makes stuff up, makes errors, if you like, that's coming from the fact that they're statistical models of knowledge bases. The solution, according to him, is to separate linguistic skill from world knowledge. And the way I would put it is exactly like that, to use role and reference grammar linguistics to identify the meaning of what's being said in the language and separate that from world knowledge. So rather than training systems as large language models have to do on all of the world's data, you don't need that data until you're going to build an application for some purpose. A bank doesn't need to have nuclear physics and chemistry loaded into its LLM in order for it to handle transactions, if you have linguistic skill. He talks a bit about episodic memory and world knowledge, so I would call that context and knowledge. And the many details to be worked out are the things that I'm talking about today. Let's compare the huge breakthroughs in statistical AI with animals, because we keep hearing that statistical AI is going to replace everything. Generative AI is so amazing, our jobs are at threat. Let's have a look at that. So first, this was something that I had a look at recently. It's a head-to-head soccer match between 3 robots. Now, if you were a good soccer player, you would be looking at the next step that you're going to take so that you can move that ball. These ones are working with the ball, but not in a human-like way. And there's a goal. That's exciting. Okay, a couple of things to notice. These robots are smaller than people. Presumably that's for balance, the size of muscles and so forth. And look, it's better than it used to be, but we're not at the point yet, I would say, where we're at any risk that these players are going to be replacing the English team, or any team for that matter. Okay, let's move on. How does an animal behave when we're dealing with similar types of problems? Well, let's have a look at this dog chasing a ball. I've just bounced the ball and it's gone behind it. Its eyes have locked onto the ball. It's racing towards the ball and it's going to leave the ground. There it goes. It's got the ball. It's like poetry in motion. This is an animal without any training and with what seems like a lot of pleasure catching a ball. There it is catching a ball with a nice red jacket. So it watches this ball goes directly behind it. Its eyes have locked onto it. Its legs are moving, front legs, back legs. It's aligned with the ball. It sees the ball as an element of context. It knows it's a rubber ball that it can catch in its mouth. It's had all its legs off the ground. It's caught it, and now it's doing a victory lap. And that ground isn't even. The background is very noisy. These are the problems that Moravec's paradox is seeking to solve. Let's compare it to robotic skills that we see with some reasonably large budgets. This isn't quite like the large language model budget, but this is something like a $190 million investment. I think it was Portland. And you can see this, the visual capability of these machines in the display. It's not human-like. And here's the famous Tesla robot with some touch sensors in its fingers, but notice that it drops the egg here. This isn't what humans do. If you're putting an egg in an egg cup, you feel it go into the cup, you make sure it's secure, you don't squeeze too hard so that you break the egg, and then you release. And finally, here's a robot where I always say, don't do this at home because it's bad for your back. So muscles and bones don't quite allow this type of motion. But it's kind of interesting to see the best robotics. So that's large language models, or that's generative AI, or other technologies of artificial neural networks being applied to problems. It gets results, but it's not being done in a human-like way. What about human language? So here on the left, you have a large language model output. I was looking for the creation of AI. As you can see in my request at Dartmouth in 1956. You can see the people there, John McCarthy, Minsky, Rochester, Shannon, and other notable attendees included Alan Turing, my hero. And here's a Wikipedia article starting about that. But the thing that I realized was odd, and I thought, wow, I seem to have something wrong, was that Alan Turing wasn't a notable attendee, and if we look a little bit further at his Wikipedia page, you can see that he died in 1954, while the Dartmouth conference was in 1956. And even it talked about machine learning being one of the key outcomes of the Dartmouth project, despite the fact that machine learning as the concept that we know today wasn't created until 1959. A better way of putting that was that this was machines that learn like a human being, that they were looking to research. Similarly, this is a large language model output from Microsoft Copilot. Notice here that I'm asking for the Wizard of Oz. Now, when a person interacts with one of these systems, the Wizard of Oz would potentially be the character from the book or the movie, but it could be something else. And what you should do when you're bringing background knowledge into context is just clarify that. Say, oh, do you mean from the book? So rather than do that context clarification, the system comes back with what looks like a really good answer about a scarecrow, a tin man, a cowardly lion. But if this was my neighbour's son, who was the Wizard of Oz, because that's what he's calling himself today, and I'm supposed to be playing along, this answer is completely incorrect. And how do you deal with that type of thing? In other words, we need to deal with context correctly, as a human being does, in order to converse like a human being does. Okay, let's move into the demonstration of the early access tool for educational use. What we're talking about is the language calculator. There's a meaning engine that allows us to recognize statements like the man is here, and what's being broken down is that representation. We have this layered element of where here, and we have the man sitting in the core. We can also do conversation, which we'll demonstrate in a moment with examples. So let's move into this analysis screen, and we'll run through what the context demo is while I talk it through. So this is what we're going to be entering, and as we run them, we're saying who arrived, I don't know, because nothing's in context. Now we've added context, Beth. Who arrived now says Beth. We add more context, John. Who arrived is Beth and John. Sue and Dana has now been added to context. And now we get the final answer. Beth, John, and Sue and Dana did. Notice that we can still ask questions that relate to the specifics, the contents of this context. So did Sue arrive? She did, because Sue and Dana did. And so we're able to extract the meaning from those elements. Did Dana arrive? Yes. Does John arrive? I don't know, but he did, because it took place in the past and we're referring to the present. So the system should answer as a human would do. Let's have a look at meaning generalization, because this is one of those topics that I find quite interesting. And look, I'm running them at high speed. You can watch it slower if you like, because it's a video. So here we're going to introduce three pieces of context: Beth eating, John eating, and Sue eating.
But John did.
We can ask specific questions like John ate cereal, yes. We can clarify things like, did somebody eat something that somebody else said no, and we clarify it. And now we can generalize into fish, for example. Cereal's not fish. We can ask the question passively, who was the cereal eaten by, as opposed to who ate the cereal. Who ate the objects? Notice that Beth, John, and Sue did. And back here, I like this one the most, who ate what? When you say who ate what, Beth the tuna, John the cereal, and Sue the salmon is one way of answering it in English. And languages are extremely capable of answering multiple questions at once. We tend not to even notice it. And this one, did Sue eat the cereal? Okay, no, but John did. So in our context here, did Sue eat the salmon? No. You could say, no, the salmon, or, as in this case, no, John did, which is the clarification for who ate the cereal. It's one of those questions in conversation. Which one should you choose? Let's go back and have another look at language. So here's ambiguity. Let's again just run them all. If you go to the kitchen, to the mat, or to the beach, you're in a different position when you finish.
In the kitchen.
Notice there, where is Sue? At the beach. But John is on the mat, not at the mat. Where did John go? It's still to the mat, or onto the mat. And where is Beth? She's in the kitchen, because just because you go to somewhere, the thing that you're going to determines how you would represent its state, because it comes back to meaning. When we talk about complex referent phrases, the destruction of the city by the Vandals was savage yesterday. Now, if you say who destroyed the city, there's no destroyed in there, but the Vandals did. And the reason we can get this is when we go into the current context, you can see that there was the destruction of the city by the Vandals. That was the embedded phrase in this full phrase. And if we look at the details of that, the way the system's working it out is the predicate is destruction, which also means destroy. It's the meaning of destroy and the meaning of destruction. So the elements here that do the destroying, that cause the ruining, is the Vandals, and they cause the city to become ruined. It's just the way the meaning's being represented there. Let's look at this one last example of who, what, when, where, how, why. These are the components, the high-level components of language. So if you bite the surfer savagely at the beach yesterday because it was hungry, we can answer questions. Why? It was hungry. We can clarify. Did the surfer get bitten today? No, yesterday.
No. At the beach. No, at the beach.
So we're clarifying information as needed. We're providing information that was there. We can clarify, no, there was no elephant. I don't know. So that's another way of answering a question that would otherwise be clarified through the context. So that's the who, what, when, where, how, why example. Now, that's the quick introduction. We actually also have categories of examples that you can see. So for example, what if you replace something in a conversation with error correction? So if you were glimpsing the dog, no, the cat the dog bit. Let's see. So that says Beth was glimpsing the dog. No, the cat the dog bit. And so this should mean Beth was glimpsing the cat the dog bit. If we check the context here, the cat the dog bit, you can see that the dog bit the cat is the meaning of the cat the dog bit. So it has correctly substituted in that information, which is good. So if we then said, let's see, Beth was glimpsing, so who glimpsed the cat?
Beth did.
It was Beth. Beth was glimpsing the dog. No, the cat. So who glimpsed the cat? So because we've resolved the correct correction here, we get the correct answer straight away. Who did the dog bite? The dog bit the cat.
The cat.
So again, we're just demonstrating that the system's able to do error correction based on what makes sense, and then resolution as a person would do. So let's jump into this. Let's jump into the meaning engine and just look at a couple more examples, because we'll pull some examples out of some text. So, for example, let's see, in medical text, here's an example. In PSS, interleukin-33 is released in the extracellular space from damaged salivary cells upon pro-inflammatory stimuli and/or dysfunction of the epithelial barrier. So this is not the type of conversational element that you would expect to hear, but what we're getting here is the predicate is released. The cause of the release is pro-inflammatory stimuli and/or dysfunction of the epithelial barrier. And we get something into the extracellular space and a patient. So there's our topic in PSS, which is this autoimmune disease. That's our topic. What we get is the pro-inflammatory stimuli and/or dysfunction of epithelial barrier causes, and I like the second part here, it causes interleukin-33 to go into the extracellular space. Now, it's possible that the interpretations of some of these can be improved, but we spend a bit of time just to show that this type of meaning-based system is capable of scaling significantly. Interleukin-33 acts synergistically with interleukin-12 and 23 on NK and NKT cells to increase the production of interferon gamma, further contributing to inflammation. So here's our meaning representation, which is, it starts with a cause here. Interleukin-33 acts with synergy with interleukin-12 and 23 on NK and NKT cells. So that activity causes the production of interferon gamma to become greater, which causes further inflammation. And in role and reference grammar, we can see here these are juncture lines. So when we go from one clause to another, the juncture is capable of sharing elements, and it sets up causative effects and so forth. You can see here that this representation of axon, it creates this logical structure where the synergy takes place, causing X, and the X is the rest of the sentence, which starts with become greater than, which causes X, which is the rest of the sentence, and then we have this further inflammation. Now, that was just showing the scope of the system, but let's have a look at conversation with the type of thing that might be useful in, say, commerce. Let's have a look at this exchange. I'll just run through them all and then I'll keep discussing it.
The man bought a car from the dealer for $1.
So you buy a car from a dealer, so there's a transfer, an exchange taking place.
Received the car.
The man did.
Who did the man pay for the car?
So you can sell, receive, pay
Who was the
for,
car sold by?
you can put it passive, sold
Did the
by,
man pay Beth for the car?
you can present somebody with
Was
something.
the man presented with the
So,
car?
so what we're seeing here
He was.
What was
is
the
a
man presented
collection of
A car.
various words and phrases used to manipulate arguments in different ways. But they all map into a common type of context. So if we look at what's been stored here, we've got some of the context from our previous interactions, but this is the one that we're looking at now. The man bought a car from the dealer for $1. That was entered into context. And we've separated out, just for clarity, that the man caused the man to have the car, the dealer to not have the car, the dealer to have the dollar, and the man to not have the dollar. And so there's those elements of the transfers just being made explicit so that we could extract further information. So that's the context that we're seeing. If we look at the JSON view, we can see that we're actually representing in a consumable format for computer scientists or other people working with computers that the cat the dog bit has this meaning of the dog bites the cat. It's a statement. We can see that the sense involved, the meaning representation is about bite, which came from the text bit. Bite is an activity with two roles. And the first argument was canis or dog. That hasn't been resolved. That's a singular positive polarity situation. We've got a determiner, and we've also got cat, whose sense is cat. So we're able to manipulate with JSON, or we can view our conversation list, which was entered there through this conversation panel. We'll just have one more look at junctures here. One of the things which it can be difficult to track is pronoun resolution. And this is because we're really focused on immediate common ground. So here we've got Beth arrived, she saw Sam, he kissed her, and then we're able to look at the resolution of the pronouns,
Wow.
she and he, her.
Did. I don't know.
So you can see that
Beth did.
who is Beth seen by, we don't know, because
did.
if you see somebody, it doesn't mean they see you.
Yes, she was. Yes, he did.
And so this looks a little bit like magic, but it's working off an extremely simple principle of context. So here we had she saw Sam. Who arrived? Beth. Beth did. Who was Beth seen by? She saw Sam, but we don't know if anybody saw Beth. So she could have been hiding, so we don't know. Who saw Sam? It was Beth. Who kissed Beth? So he kissed her. Now we have to work out he is probably Sam and her is probably Beth. So Sam, who was she kissed by? Who's she? She is Beth. Who is Beth kissed by? Sam. Was Beth kissed by him? Sam, yes, she was. Did Sam kiss Beth? Yes, he did. And the use of pronouns in answers is really highlighting the fact that we have this natural tendency towards the immediate common ground. If there's two players in context, or there's activity that can be tracked by who the last reference was to, then it's quicker to say he did, she did, rather than going back to the full-on referent. And just to show you that it's not magic that's taking place here, we've got Beth arrived. When she saw Sam, the meaning representation of she saw Sam has been clarified. We had that, it's technically called a location in our thematic relations, but here we've got Beth saw Sam, which allows us to get the correct answers in the query. He kissed her. What do we see here? So Sam kissed Beth. So by resolving the pronouns, we can see the pronouns here in the representation. By resolving them in terms of our thematic relations, we're then able to do the work necessary to carry on a conversation. And those types of things will be very helpful as the language understanding part that splits language from knowledge, that then allows us to build improved chatbots or improved conversational AI that is taking what people are saying, converting it into what they mean, and therefore accessing other systems in order to provide useful capabilities. Okay, so I think that's our demonstrations for now. Let's get back to it. Let's continue with the solution. So I've shown you what the system can do, but let's have a look at brain science or Patom theory in a little bit more detail. Patom theory comes from the concept of pattern atoms, which make up the basic building block of a brain region. Atoms of patterns that connect between the different senses and or motor control in order to control an animal. I like to say that the brain is the final frontier in science because we know almost everything in some level of detail. But if you look at the brain regions on the right, we know if you have these types of brain damages, you can be very debilitated. So, for example, if you have the V5 region damaged on both sides of your brain, you lose the ability to recognize motion. So if you were to see a car coming towards you, you would see the car moving. Well, maybe you wouldn't see it moving. You just see it frozen, and then you'd see it vanish. And then it would appear closer, and then it would vanish, and then it would appear closer. So somehow our brain is able to do that. And faces, if it's an effect of your on your inferior temporal lobe, your ability to recognize faces can be lost. So people with this type of damage have to speak to somebody, listen to their voice in order to recognize them. So there's something about visual faces and these other specialized visual capabilities that people can lose depending on the type of brain damage. And how would you explain that with a computational model? In Patom theory, we explain it that each of those brain regions is matching patterns that are provided to it from previous regions and subsequent regions that it can use for top-down and bottom-up recognition. It's just a very different approach that seems to explain how animals are able to do the amazing multisensory capabilities that we see them do. Here's some evidence for how the brain actually works as a recognition machine rather than a recall machine. So if you ask somebody, and this is Robert Epstein's work, and there's the article. If you ask somebody in America to draw a $1 note from memory, they would draw, or they could draw something like this. However, that's not what any dollar bill looks like. If you then give them a dollar bill and say, can you now redraw it, they're able to come up with this. So that's by making comparisons between the dollar bill you see and the page that you're drawing the dollar bill on. My argument is that this is an example of Patom theory. We're drawing something that's sufficient to recognize all of those examples in the future. It's like a template. It's a pattern that represents the sum of all the patterns that you've seen in a simple way so that our brain doesn't need to exert much effort in order to recognize things. And this takes place across all senses. The point about the brain being symbolic versus statistical can also be addressed with this. It's not symbolic in that we're taking photographs of the world and storing them. A better way of thinking of it is we have a simplified representation, never of any specific example, but sufficient to recognize it later. How does the computer work? Well, in the CAT, C-A-T, in Unicode, those are the numbers, 43, 41, 54. And those specifically mean, if you know that it's Unicode, capital C, capital E, A, capital T. But what the brain has to do is recognize the capital C, the capital A, and the capital T, and then store it somehow. So we need to move forward from how do you now put this into a computer, which obviously is a problem if you're trying to represent this on a computer. But this is an example of data encoding, right? There's our code, Unicode. And by encoding it, you're able to manipulate it. But our brain has to deal with the real world with physical senses. It's quite different. And again, how do we do that? Well, Oliver Selfridge, the English MIT manager of, I think he was Marvin Minsky's supervisor, back in the 50s. One of his examples is this, and you'll notice that the H or the A in the and cat are exactly the same thing. They're drawn exactly with the same pixels. And yet a lot of people can probably see the cat written there. But it could actually be Tay Chut. It could be some name of a company, for example, an acronym for a company. And the only way you can determine what this means is either, well, you can't work out the letters and then the words because it's still not enough, and you can't work out the cat because it may well be Tay Chut. We always need context, and sometimes you just have to ask questions. Finally, if you're a computer system and you want to store that H character, you have to resolve it. You can't put it in a memory location as an H and an A, so you can't double encode memory locations. So there's something fundamentally different about the brain versus the digital computer. Okay, what's a visual pattern look like? Well, if you want to recognize a C, there's a bunch of Cs, and somehow we want to recognize all of those in a visual region of the brain, and then recognize it as being part of the same set. It's the letter C. There's other patterns that we need to recognize too. Is it a capital, etc.? But that's the visual set, which I'll call a snapshot. And here, when you recognize on the left-hand side the C, we can then connect that to other patterns that we learn on this side to create CAT for cat, ACT for act, and just with 3 elements in a sequence, we're able to link these elements together to form something far richer. And you'll notice that this potentially could be only 3 neurons or 3 neural columns that are somehow working with those elements. And it's a very powerful and concise system. So it's a different way of thinking of memory. Let's run through an example. We want to recognize these Cs. Now that we recognize the Cs in visual memory, and we can also find these other attributes like, which are capital letters, small letters, bold, italics, and so forth, we can link it to this green box, which is our meaning representation. So one of the meaning representations is C, that's a kind of letter, and another one's capital, and we can combine those things for the particular example that we're working on. So we add a few more letters, T's and A's. Sorry about the cat use, but I like cats. So here we see as a sequence CAT. Now this visual sequence can map to a different meaning, cat. We don't need to start with a CAT. We can just go from CAT being here from visual memory. So different meaning between C as a letter and cat. Once we've got meaning, we can now connect it to hearing. So we've got C and cat connected to the letter C versus cat, respectively. And now we're starting to get into the multisensory domain. But also because we have meaning, we can now connect it to speech. The muscle control necessary for an animal to produce sound, they need to be synchronized. There's a lot of muscles in humans. We have to breathe correctly so that you can hear the sounds appropriately. Let's move on to what we would see if we're looking at a brain. So what we're seeing here is that CAT, C-A-T, comes into our visual system, and we can see it. The occipital lobe has activity. It projects to other areas of the brain. And the question is, what's going on? And if you just look at this unlabeled model, which is all we get, it's perplexing. But if we were to label things here in the visual cortex, well, perhaps what we're recognizing is, well, that's a letter T, a letter A, a letter C. In the case of the capital CAT, maybe there's an H that we're recognizing and an A that we're recognizing, and we're projecting that forward into the sequences. So remember, these sequences are learned in advance, and they can be validated against what we're seeing. So there's this top-down, bottom-up that's constantly in use, which allows for us to recognize what we expect to see and make good decisions about what we see based on what we already know. So let's move on to learning language based on the fact that we have that technology that we can exploit for different types of applications. One of the things that I'm involved in, we have a startup that's looking to use brain science and language learning skills to help the 500 million people a year that don't correctly become fluent in a language, even though they've bought an application to learn another language. So what is a solution? Well, our partner Chris Lonsdale has this model here where we go from brain soaking, whatever that is, to comprehensible input, the face phonics. Let's have a look at brain soaking and face phonics to get a feel for how we can emulate how a child learns language. So when a child starts to hear language, their brain is doing what looks like this brain soaking concept. So as they're hearing language, their auditory cortex is receiving the signals from their ears, and those signals are going to auditory cortex that its job is to make sense of sound. And there's a central area which is picking up the primary area, and then there's some regions that surround it that get more and more detailed, and then they project to other regions. But interestingly, brain soaking could simply be training the auditory cortex to recognize sound by listening to the sound that you want to learn. That's all you're doing. That's the exercise. A different type of example is face phonics. So in face phonics, what happens is you can see somebody speaking the words of the language, you hear what they're saying, and then you can say it while you're being recorded. And so the face phonics example allows you to say things. You can hear it as you're saying it, of course, but you can also then have the system repeat back what you've just said. And by using the face phonics concept, you can start to generate your speech production capability. So this is a way of exploiting brain theory and brain science. Let's have a look at what brains are able to do with patterns of the type that are used in language. So here's a written code, NE1410S. And if you expand that, you see we've got northeast, we've got 1410, we've got, maybe that means south, we've got E sound, E, we've got the N sound. What do we got? 4 plus 10, there's a 10 there, there's a 4. But if you wanted to decode that, you can keep working on it. But this is the message I was trying to get out. Anyone for tennis. Anyone for tennis. And there's no reason that we wouldn't recognize that instantly, except for the fact that our brain's not a supercomputer. So when we're talking, we're not processing all this stuff. What we're doing is we're recognizing, in this case, you need to recognize that sounds like N, that sounds like E, that sounds like 1, that sounds like 4, that sounds like 10, and that sounds like S. Anyone for tennis. But it's not processed in real time like that. So what's happening instead is we're able to take this combinatorial explosion and work it out. But language isn't working like a new word. All it's doing is it's recognizing the components and putting them together. So we need to get rid of that combinatorial explosion with language so that it works in real time. And the linked set from Patom theory does that. We only have to link to something when it's known. We don't check for things that aren't known. Now, in fact, this is very similar to the frame problem of AI, where human experts don't even bother with certain things that could be relevant when they're solving problems. Okay, but what's language? Is it millions of words or billions of words, as in big data, or is it something else? Well, interestingly, if you look at the world's languages, take English, for example, and you take every word that's stored in the internet, the input to a large language model in English, for example, you would find that 50% of those words are comprised of something like 66 words. It's very small. And why is it that 50% of language are 66 words, and once you get to a couple of thousand words or 3,000, 4,000 words, you're not only fluent in the language, but you're very effective? What are those other words supposed to be doing? Why can't we just do a small number of words if we want to learn the language? Well, if you look at the top 100 English words, you can see some patterns here. So we have the auxiliaries, is, has, does, and there's only a few predicates like seeing and come and go and give. There's pronouns and possessive pronouns, and all the question words, a couple of modals. So what's going on here is that the building blocks of language are used a lot because they're helping us identify immediate common ground. They're helping us identify context. And so by starting with learning those contextual environments, you're then able to converse with people. You don't have the vocabularies that native speakers have until you learn those as well. But if you can learn what allows you to interact in the immediate common ground, you've got a really good start to the language. Now, the breakdown, rather than the parts of speech model, I'm advocating for meaning-based elements, semantic predicates, and reference. And on the left-hand side, the predicates of the layered structure of the clause, of the sentence, you've got the eater ate a meal, ate, limping, buying, bought, exploded. Those are the obvious predicates. But what we found through practice and experience is that the categories that apply to a predicate, the arguments, are also worth identifying as predicates so we can generalize from it. What's an explosive? Well, an explosive is something that explodes. So here, the explosive exploded, we can recognize the word explosive also as a predicate. Actually, the word the should be black. It shouldn't be a predicate. On this side, reference are different, like they're names of things and specific examples, the Wizard of Oz, for example, and they represent things. But predicates, the additional information, like I was handed an explosive. Oh, maybe that's not good because why? Explosives explode. Oh, what does that mean? Well, if it explodes, I could be injured. So here's a different view of language to the one that most people talk about. Here are the 100 index words like pronouns, proforms. So here, there, he, she, it. And things that are purely contextual like hello and yes and no, which don't mean anything outside of a conversation. And then we've got the category words. You know, I'm showing here cat, dog, tractor, shoulder. These are things that you can use to make up lots of interactions with people. So this is the base of language, and then down here we've got the infinity. So there are an infinite number of names to consider. Julius Caesar, for example, is a specific guy that was alive in the 50 BC, and we need to know that particular proper name to get by in general life, so that you're not ostracized for not knowing a little bit of history. But all of these different types of particularly reference, so people, place, company, streets, is the extension of language. But you can add new things to language very easily, provided you can access the core words that are up here. Let's just quickly look at why linguistics hasn't been solved before. Why don't we have natural language understanding systems? And it's because the idea of rules and word statistics just isn't enough. It's too simple. So what I'm showing here is the Roland reference grammar linking algorithm that connects syntax or words in their word order. It links that to a semantic representation, and it does that with discourse pragmatics or in context. But here we've got the Chomsky 1956 formal linguistics model that was focused specifically on syntax. And here we've got Firth's work, which is around a word is characterized by the company it keeps. And that's the basis for transformer architecture and the focus on word sequence that has been around now since that time. Let's have a look at Chomsky's syntactic structure from the 1950s. The independence of grammar. So the fundamental aim in linguistics to analyze language L is separate grammatical sequences from the ungrammatical ones and then study the structure. So if you're going to study the structure, what is that structure? Well, it's the parts of speech in the tree that was considered to be important, and that is the basis for computational linguistics, which continues through to today. He then wrote that grammatical isn't the same as meaningful or significant. Well, okay, that sounds good. And the example is colorless green ideas sleep furiously versus furiously sleep ideas green colorless. So a speaker of English recognizes colorless green ideas sleep furiously, and you can't argue with that. I can recognize it. So what are the ideas? They're colorless and green. What do the ideas do? They sleep. How do they sleep? Furiously. Now that doesn't make sense because that's not how the meaning of those words operate, but we're picking up a pattern there. But the structure that he's looking to create is relating to this. The grammar is associated with constituent analysis based on parts of speech, verbs, etc. And let me just show you how I falsify that. So if we say colorless green ideas sleep furiously, we've got adjective, adjective, noun, verb, adverb. That's grammar. If we then take another sentence like the running race ran very quickly. So there's a race where you're running and it took place very quickly. It ran through very quickly. So in this case, we've got running as an adjective, race as a noun, ran as a verb, quickly as an adverb. So we can now substitute those words into this structure, adjective, adjective, noun, verb, colorless green ideas sleep furiously. And this must be grammatical because if we're saying that studying the structure of language like this tells us that it's grammatical, well, this must be grammatical. But when I read running, running, race, ran quickly, it doesn't work for me. My brain's not saying this is English. Running, running, race doesn't look right. And so there's something more that's required because you can't build a system based on this being grammatical and then find out it's not grammatical. The other reason why NLU isn't popular today is the extension, where NLU is, according to complexity theory, this was done in the 1980s, it was determined to be LFG anyway, NP-hard, so lexical functional grammar that came out of Stanford is NP-hard, meaning that as the size of the problems get bigger, it's an exponential effort to solve the problem. And that's not good. It basically means that language understanding taking place in real time, in theory, isn't possible. Well, I've actually spoken to experts in the field that tell me that the work that I can demonstrate is operating is impossible, which by definition isn't sensible. And my best example is humans learn to speak language, so it's obviously possible to do this in real time, and so I'm not sure what the problem is. So for anybody that's thinking, well, I can't study NLU, I have to study statistical AI or generative AI because NLU is impossible. It's not. And it's just one of those things in the history of science where everybody believes something for a while and then they're persuaded to better possibilities. Now, let's go into a bit more detail about parts of speech in computer science, because as a computer scientist myself, I often was confused about what I was being taught, and things haven't changed much since I was first studying my Bachelor of Science, majoring in computer science. So here's an example of a knowledge graph and an entity relationship diagram. It comes from Wikipedia, and here we can see Predator 1987 had Arnold S. Schwarzenegger was the star, and Arnold S. Schwarzenegger is governor of California. So the thing that strikes me is that these look like the predicates, so produced and star of. The 1987 looks like a time, looks like a year, and Arnold S. Schwarzenegger is a particular person, not a name, so we need to refer to the correct Arnold Schwarzenegger. And when that person was governor of California. When was that? So there's information it would be nice to know. And the governor of California, that's the body California, whereas the capital of California also refers to the government of California, but Sacramento is also a place. So the thing that doesn't look right here is we're not talking about meaning, and this is very simplistic and not sure how well it generalizes. In fact, I know it doesn't generalize in a lot of cases. So ideally you want to get the words out of this converted into a meaning representation and then flesh it out a lot more. If you say Predator 1987 as a person, I can tell you what I think they mean. But the whole point of creating a knowledge graph that you can use with machines is to make it unambiguous and make it a very rich resource that you can use for all sorts of applications. And at the moment, this is limited. This is the page that talks about entity relationship diagrams. You can see that they're talking about nouns and different verbs and adjectives, adverbs, so again, parts of speech. I put down derived nominal here because there's a whole category of words where we're embedding sentences inside a sentence where we change from verbs to nouns in order for that to take place, and we should account for it. So in the help for this, it says entities can be thought of as nouns, like computer employee song. So what they're really saying is that don't think of them as nouns, think of them as reference. That's what they actually are. They're things. And relationships you can think of as verbs linking two or more nouns. No, think of them as semantic predicates. And by doing that, we're then enabling this whole system to work based on the science rather than having to have people translate what's going on. For example, here's two roles, artist, perform, song. So we've got a verbal phrase. This is a simple sentence. The artist performed a song. So there's the verb. But here, the performance of a song by the artist, that's a noun. But the song performance by artist is still the same representation. So we need to get away from that model of syntax being embedded into a semantic relationship, and suddenly we're going to get a lot more power. Now, because performed and performance are different words, but with the same meaning, we want to put the meaning in here so that we don't have to specify whether it's the noun form or the verb form in our meaning representation, which is what one of these representations is all about. There's in RDF&L, this is just again looking at the big and old knowledge graph representations. Notice here we have subject, predicate, object. So the subject in an active or passive sentence is going to change. It's better to use the terminology of something like actor, undergoer, or one of the appropriate thematic relations that can simply show this relationship. Now, rather than triples being subject and object, some predicates have 0 arguments. So, for example, it's raining. It doesn't mean anything, it's just raining, but English doesn't allow you to leave the it off. Some predicates have 1 argument, some have 2, some have 3, and some have more. So rather than storing things like this, what we want to do is decompose it into its meaning representation. And if only we had a science that did that. If only, oh yeah, okay, we're coming up to ROG in a minute, and then you'll see how ROG does that decomposition so that you don't have to think about it as a computer scientist. Now, rather than using this triple model, let's use meaning. So if we have, these are sad examples to think about, but the animal died. What it means is that the animal has become, so it wasn't before, but now because it's died, it's now in a state being dead. And that's what the animal died means. But this completely different word, killed, this is a causative predicate. So now what that means is that the man does something which causes the animal to become dead. So by having the same thing that we use twice, become dead, now we've got generalization starting to take place. If we can identify our predicates accurately, we also know that killed is causal, and so we now have the causer of that activity. These are extremely precise ways of representing meaning. And the next generation of knowledge graph should be based on the semantics of our brain plus the meaning of what we're saying. So let's move into RRG linguistics. I think this is the time. So here's RRG and the semiotics model. So back in 1900, if you were talking about language, you may well have been thinking about how semiotics, or the science of signs, connects to meaning through some sort of interpretation. So Peirce was, back in those days, discussing how semiotics is a key to science. And I think that's probably a better way of, even today, thinking about language. Because this sign can be written, as in the case of reading, or it can be verbal in the case of speech, or it can be tactile in the case of Braille. It doesn't matter what the sign is, as long as we're able to then connect to meaning and interpret it correctly in context. And that aligns nicely with the role and reference grammar model, where we're going between syntax and semantics, or words and their sequence and a meaning representation, and then back in line with context. And here's our predicates and reference that live at the meaning layer. That basically today we tend to see all of the sciences factoring out discourse pragmatics or context, and factoring out the semantic representation independently to the words and phrases that make up the language. So let's just drop back in history, because I think this is a good way of explaining it. So in 1956, Zelig Harris, who was Noam Chomsky's supervisor from memory, he identified that sentences make up language, and there's two types of sentences. There's simple ones and complex ones. And examples of simple sentences are: the man is tall, the party is in an hour, the man will go to the party. There are three simple sentences, but you could repackage them with transformations. So the man is tall can be tall man, the party starting in an hour is a phrase that represents that, and the man will go to the party. Those three sentences get combined to the tall man will go to the party starting in an hour. And this is much easier to say, much less effort. And so by repackaging simple sentences, our languages become much quicker at communications and much less effort. But however, if we could simply identify all of these things and the transformations that allow us to embed them, and then recognize both accurately for that language with tests, maybe on a computer, well, then we've got a really good system. And the model here, this is the layered structure of the clause from role and reference grammar, and this is a reference phrase which allows us to embed those that repackaged sentence in a way that we can then put it back in as one of these elements of a sentence. So this is from Harris. Notice that he talks about nouns, verbs, prepositions. So this is the part of speech model. He then talks about the transformations, like you'd normally say, I like this, but you can equally say, this I like. Or this one, the bulbs are from Holland, sentence, bulbs from Holland are pretty. That's a phrase that you can embed in something else. So that's the concept of transformation, sentences to phrases. RRG uses this same model, but it then adds meaning and context to make the interpretation far richer. And by not factoring out meaning and context, now you've got everything needed in your scientific model to make this an empirical system. Here's some examples. So here's a core in which the predicate is happy. So inside the core, we've got happy surrounding she. In the garden, John is in the garden, the party is tomorrow. We've got John in the core, or the party in the core, and then when and where is being filled in this simplistic way. But we can also put in basically a whole core, like he walked the dog yesterday. So he walked the dog is in the center, when yesterday. Or he gave it to them because it was valuable. Why is being put on the outermost layer. And this way we're able to provide our predicates in a particular order and still interpret them correctly, because we're matching a common semantic layered model. And obviously we can plug in these as a sentence or as a phrase inside a sentence, and we have to track both correctly. But that's what context helps us with. One of the other things that ROG does, which I'm not talking about much today, if he was eager to please, you're taking the he forward to the second phrase, so he pleases something. Or if he is easy to please, you take the he forward, and then it's he becomes the undergoer of pleased, so he was pleased by someone. In practice, to do this in scale, one of the things that we found, and this was a patent from 2015, when you take a complex sentence like the cat ate the rat continuously, slowly, etc., what we want to do is test all of these examples and consistently map it to something. So for English here, we identify syntactic elements, and we label those syntactic elements. And great, you've identified some things with labels. The thing that matters, though, is when you try and map it across on the right into its semantic representation. At that point, with predicates determining arguments, you can ensure that at least this proposed sentence makes sense. And you can also then apply the correct layers so that the relationships of these different syntactic parts are shown in the correct place. So this two-step model allows us to match very complex sentences in real time, as we are able to remove the things that just don't make sense because predicates determine arguments. All right, let's move on from that theory to looking at what's required to build a dictionary so that natural language understanding can work. Okay, well, we started with the concept of predicates and reference. So predicates are things like relationships, so destroy, which is a verb, destruction, which is a noun, or party, which is a noun, but it's some sort of event. So they're treated differently from reference, which are the things. I'd like to occasionally point out that language is very complicated and there's lots of problems that we've had to deal with. Notice that in a syntactic model, cats is plural, right? So why can I say cats is 4 letters? Cats is 4 letters, but cats is plural, so it should be cats are 4 letters. What we're really saying in that sentence is that CATS is made of 4 letters. Cats, the word, is 4 letters. And because we're talking about the word, it's metalinguistics, and we're able to do that. And your linguistic model has to deal with that. I don't know how you're supposed to deal with the recognition of the meaning of cats being independent to the actual sequence of words without having a meaning-based system. Okay, so what do words mean? I like to say semantics is the last ontology we'll ever need, because predicates are these things that relate, like they'll relate in time, space, and reason. That's that layered model we just looked at. They also can be combined with other elements, like pick up isn't the same meaning as pick, and up can be elsewhere in the sentence, but we're still relating things, and we're using the predicates to determine their arguments to accurately determine if it could make sense. Reference are a bit different, and the dictionary definition of, say, IBM would normally be, well, it's a company and maybe give us some information. And so if you think of it, there's a few different types of information that applies to a referent. So you can say it's a company, so that's a hypernym relation or is a relation. Had 23,000 global employees in 2024, that's a meronym or has a relation. And then here's your normal predicate relation, like makes a range of computers. IBM makes a range of computers, or works on quantum machines. So we can, if you can identify IBM uniquely in language, store it as a referent, identify that there's information about that that's relating specifically to that referent. You can then build up this dictionary content through interaction that looks very similar to the way humans build up this knowledge. So you can imagine going to science and learning about, for example, an atom, and you start with only knowing that it's a type, it's a thing. So there's our hypernym relation, atom is a thing, and then as you populate it with it has electrons, one or more electrons, and all of those details. You populate meronyms and predicates. It makes up matter, for example, for atoms. This allows us to learn language the same way that a person does, and it allows us to build a dictionary repository that is going to then allow us to converse the language without having all of that complex knowledge in other forms that we've learned through reading other people's books and so forth. But does it work? Well, going back to about 2006, I was looking at how to best represent dictionary information, and when it comes back to hypernyms, meronyms, and predicates, well, that seems to be what we see in dictionaries. So here's the dictionary definition from WordNet. All of these are from WordNet. We start with Michael Faraday, my distant cousin, and the definition is the English physicist and chemist. So what's a physicist? It's a person. What's a chemist? A person. So we're saying that, and English is describing where he's from. So Michael Faraday is a person. So there's our hypernym relation. And now that you know he's a person, there's lots of things that people do that you can now assign to predicates. People discover, certainly physics and chemists discover things like electromagnetic induction. And we've got the date that particular event took place. So we have here a hypernym, we have here a predicate. What about cat? You know how I like cats. So in the case of a definition for cat, it's a feline mammal. So it's a mammal. We're immediately identifying a cat as a mammal. There's a hypernym. What about this one? So cat, a spiteful woman gossip. So it's a woman. A cat is a type of human female. What about this type of cat? Or quat, or it's the leaves. So it is a type of leaf, and then we've got more detail there. And down here, caterpillar, it's propelled by two endless metal belts. So we've got a predicate here that's extending the fact that it's a type of vehicle. So this type of information, just coming from the dictionary, is going to be extremely valuable in the future for meaning-based systems, because you can define this dictionary once, and the wealth of information that goes into the definitions, of which we already have a lot of experience, are going to be very valuable to typical conversations between people. And all these things get used in context. So as predicates are determining arguments, cat can be resolved because, for example, the cat has treads. The fact that it has treads, you're going to have to exclude cats, and cats as in the true cat or the lion, because tractors have treads, the other ones don't make sense. Cat of nine tails, which you could call a cat similarly. Okay, so let's go back to the RRG relationship between words and their meaning, just to get a better feel for what's in which category. So here, in a language, we have transitive C, which has a third-person object and a third-person subject, and then we've got the man, the woman, and the way that language will interpret it is the woman saw the man, or the man saw the woman, depending on the context. So this word here, C plus, looks like, well, third-person object and subject. So she and him, or he and her, whatever the actual pronouns are that you would use to populate that in English, that's all part of a word. So words can be very complex, and then the sequence, the phrases are also part of any language. So there's a lot of variety here at the language level. But down here, the argument is that, in this case, the man gave the dealer the car. We have this representation. The man does something which causes the dealer who didn't have the car to have it, and the man who did have it to not have it. And so there's a lot of information in giving the dealer the car. And this is the best way for us to operate off language in the future. We convert the language into its meaning, and then we operate off the meaning in order to do things like put up the window, or put the window down, or transfer money. by doing this in one language and recognizing in a different language the same meaning, we've already tested that the system is going to work. So we're able to take out that localization problem that comes with language systems today. And it's a very expensive problem to solve. On this side, this is talking about how we use context in conversation. And it's incredibly powerful. It's incredibly concise and accurate. It's precise. When you say Taylor married Ridge, with 2 words, you can change Taylor or Ridge as the person who's listening. If you say Taylor married Ridge, no Brooke, that would mean Taylor married Brooke. But if you were to say, I'll have to use 3 words, Taylor married Ridge, no, Brooke did. In that case, Brooke married Ridge. And so with only a couple of words to clarify that, you're able to change the meaning in conversation very precisely. Okay, so what are the building blocks? Well, complex words like it to her he gave, that is a word composition. English doesn't do this quite so much, but we still have like you've got gave, given, so we're putting give, given, we're putting an N on the end or the N sound on the end of words. So there's some composition. I like this one more. It's a lot more detailed. So we've got word composition. We've also got phrase composition made of words. So if you say the Wizard of Oz, you can work out what that means literally a wizard, and it's from Oz, and so you can pull that together like normal language. But equally, you can match that sequence of words, the Wizard of Oz, into a specific thing independently to the words that comprise it. And one of the tests that I would do to show that that's a sequence of words is if you change that to the Wizard of Australia, for example, if Oz means Australia, the Wizard of Australia is not the book or the movie anymore. Like, you might be able to say to the person, do you mean Wizard of Oz? But by default, it's definitely not the same thing. So there's literal phrases of words that are important to know in order to understand the language. Equally, we want to decompose words and phrases into much simpler form so that we can rapidly recognize language. So rather than the parts of speech model, which uses these rules, if we decompose the word I, and it's a referent, we can recognize somehow that it's a valid reference phrase in RRG, and it's first person, and then that saw is a predicate, it's a state, and it's got 2 roles, and it's got its tense, past tense, and in this case, and it's also got first person capability. Well, now in English, those first 2 are recognized as a phrase, I saw, and then we've got this other argument, the object in syntax, or the undergoer. So here we've got the fact that we're looking for a referent and a valid RP. So this sequence here of elements, there's simpler versions that we've developed now, but that's just showing the principle. This type of phrase can be keyed off referent, so every referent we can just check, is this valid for this particular sentence? Is this valid for the sentence? And so we can quickly pick up syntax, and later on we can quickly pick up the semantics. And so that's the principle of the building blocks for language. Now, there's a bunch of predicate classes that Roland Reference Grammar talks about. It's basically built on states like colors, for example, so blue is a state, and activities like eating and walking and so forth. And they have one or 2 arguments typically, but there's a bunch of different ones and more precise ways of expressing that particular predicate. There's additional elements that come from the language. And then how many arguments does it have? Well, 0, 1, 2, maybe there's additional arguments. The additional arguments get identified through prepositions and other techniques, typically. So those are the predicate classes, and I like to show how those work in a real language like English. So in the center of this, we've got the word see, so that it's the meaning see. And to use it quickly, we want to be able to say that I want to cause them to see, a causal form, and we've got a word for it called show. So in this case, something causes somebody to see something. Show. There's another form, like if you want to watch something intently, you can't see something intently, but you can watch it intently. So now we've got watch here, which is an activity. Or it could be something where you're looking for it, you don't see it, and then suddenly you see it. It's spotting it. Or you see it, then you don't see it, you see it, then you don't see it, so you've only got a very brief look at it, and now you don't see it, then you've glimpsed it. So our language is being built on these components that Roland reference grammar. I don't know if I said that. There's the most popular one, number 11 in English, C, the state. So we're able to use these predicates in a number of ways just by knowing which word in the language identifies those extra pieces. It makes the language much simpler to speak. Equally, that I've just looked at words, but equally there's a whole bunch of different ways of combining words so that we can make up more complex ideas. I'm just dropping to the bottom of this one. These are the interclausal semantic relations. Simultaneously, there could be activities taking place. So you're playing the piano while also playing a harmonica. That would be represented like this. Or you could have a couple of things happening in a completely distinct way. So you could be walking down the road and someone else can be hopping. And they're just two different things happening and they're not connected to each other. There's a whole bunch of relations and I won't go into detail today on that. How do we solve ambiguity? I mean, ambiguity is everywhere. Look at this. So is it the old man that saw John's purchase of the Porsche at the stadium yesterday? Was it the purchase that took place at the stadium? Or was it at the stadium yesterday, the old man saw John's purchase of the Porsche? And, well, there's this concept by, called, it's a Gricean maxim, Grice's maxim, that says that we speak in a way that's not ambiguous. The whole point of speech is to communicate ideas. And if you say things that are hard to work out, you force the other person to ask you a clarifying question, and that's not good. And so the principle here is that people tend not to speak like this. If they do speak like this verbally, they can put emphasis on the appropriate words so that you know what they're saying. But there's also ways of restructuring that sentence so that it's unambiguous. So, for example, if I said at the stadium yesterday, the old man saw John's purchase of the Porsche, that it's applying to the seeing unambiguously because we're putting it into the pre-course slot of the sentence rather than referencing this embedded phrase. But there's a whole bunch of things that we can study just based on this concept of simple and complex phrases. Okay, in order to make a language-based system work, is each language needs to have the sentences that make sense, which are determined by those predicates, predominantly plus that layered structure of the clause. We have to build something that we can test. So the predicate classes, as they vary, we need to build tests for all of that and then add vocabulary and test it. And that resource should then be available to anybody that wants to do natural language understanding. So the principle that we use in computer science is work out what your model's going to be. So I'll have a predicate class, and regardless of the predicate class, I'll allow these other predicates in the layered structure to apply, and then I run tests. Now, in computer science, if I do unit tests and integration tests, I can slowly build up a system that is highly accurate. And as I add new vocabulary, if I run all my old tests, I'm then ensuring that my system has data integrity. It works correctly. So this principle is going to allow us over time for multiple languages to keep mapping from those languages into a meaning repository and then use it to do all sorts of things that will work across the world's languages. And testing is central to all of that. In fact, in computer science these days, the concept of running unit tests first and running test-driven development, and also incorporating integration tests later on. That's the principle that we like to use, which isn't an easy thing to apply when you're working with data, because the data can actually break all your tests. It's not testable in the same way. If we keep adding new vocabulary to language, all we have to do is keep adding tests to make sure that if we are introducing the same word or a different meaning, we're not going to corrupt the system before we release into production. Okay, and at that point we move on to Beth. Beth, you can take over. Thank you.
So if this has inspired and got you thinking about what would the next generation of AI look like, what would trustworthy, sustainable, accurate AI and communication with machines look like in the world's languages, I would encourage you to think about some research as you go along. You are students, you are professors, you are researchers for the next generation of what comes out and potentially benefits society, rather than what we might be doing or some technologies might be doing at the moment, which is taking us down a questionable path about its overall benefit and equitable benefit for society. So as co-founder with John, next slide, John. If you would like to collaborate with us, I've got some suggestions, or we've got some suggestions, and we're being asked about this new science and how we can collaborate to bring this new science to life in engineering projects for the world, for society's benefit. Think about the sustainability opportunity for it, for enterprise software. It's a deterministic language AI for enterprise software. It is transparent, it's accurate. So what would that effect be, impact for digital assistants, if we can trust what we're saying to a machine and it can understand us in over 6,000 of the world's languages. The other project John mentioned, we're looking at with a famous language educator, is how do we improve and supercharge human learning when it comes to learning another language. It shouldn't be hard because we all learned our first language. So how do we learn another language as easily as we acquired our first? So if you look at the speechgenie.co site, there's more information there and you can follow the project along. The system that you saw John demonstrating today is available or becoming available now as we're being asked by people in universities, how do we get access? How can we look at what you're doing? We have an opportunity for an early access license so that you researchers can do the research on this new science, how it applies to computers, and what are those benefits, how does it compare with today's LLMs, for example. The book that John mentioned, if you want, that is available. There's links and you'll see them in the slides that will be provided. The book is available online on Amazon. We have some copies here if anyone's interested in getting a subscribed one while John is here and is 10,000 kilometres away from home, so he said. Thank you, and Kulvinder, did you want to open for questions?
Yes, certainly. I'll just come round that way. Okay, so thank you so much. There was a lot in there in terms of language, in terms of the limitations of large language models, and obviously we need to be looking at trustworthy AI. So let's just look at, so first question, and then I will go to the online audience, is where do you, John, if you could come over here so that we could, so where do you see the current AI space, first snowballing down, and how and what form and impact? What's the nature of that impact?
Well, I think the next generation of AI is going to be tools that work with people in a very natural way. For example, with language, one of the weaknesses of a large language model is it can produce a response. But what you care about to do something is, what have you asked for and what does it mean? so that you can go to some back-end system, go and do some work, present it back to the user and continue on. So you can imagine if rather than going to a banking website, you key in all the details, if you could simply interact normally and say transfer money to my check account, if it knows what your check account is, or it can ask you, do you mean this account number, and if it's just tracking the way you'd like, well, you're in business. It's going to revolutionize how we work with machines. So for me, we did a project with One World a few years ago, and they had this unsolvable problem, which is all these legacy machines that were built in the 1960s and 70s to ensure that the pricing is fair in the airline industry. And so we wanted to have a front end to that in order to help people do a round the world ticket. And what we found was there's not many questions that you need to ask somebody in order to get the right answer. So it's not an open domain problem where you say, give me your children's names and your home address and all that. You can get a round the world ticket by simply saying, where do you want to go? And that's a very contextual question. You can just read out the places you want to go to. It can then organize how you would put that into a travel itinerary. And you're simplifying the problem significantly. And so I see that by using new technologies that get to the meaning of what's being asked, we can revolutionize AI over the next few years. But first, we have to deal with the fact that there's a lot of interest in LLMs that is sucking all the oxygen out of the room at the moment.
Okay, thank you. Okay, so from the audience, from the audience in the room, any questions? Yeah. Okay, Deva, you can go
In
first.
terms of the available technologies, how trustworthy they are, and if they are, how trustworthy and sustainable they are, and in case they are not, they haven't reached the level that we want, is there any way to reach there? How can we get there?
Okay, so the first bit's on the sustainable and the other is on the trustworthiness. So with large language models, they have two weaknesses. One is they use GPUs, and they put them in data centers to centralize all of that, and they're not sustainable because they're hugely expensive to run. And the more the system scales, the more expensive it is to build those things. And the weakest part of that technology is the lack of accuracy. So it's a statistical model of every book and resource that's on the internet, but it doesn't store the actual results. So it's statistically working through a response, and it creates errors, and it's unsolvable. So today's AI has this unsolvable, expensive problem to deal with, but it's also got the richest people on earth pushing it. And so we're struggling at the moment that once you get Google and Amazon and Meta all working together and all lobbying governments, they're very keen to do what they're being asked to do. But at some point, they're hitting this unsolvable barrier, which is you put trillions of dollars into something that can't make any money because it's not reliable. At some point, you've got to back off. And then the hype deflates, the bubble deflates, and lots of people are going to have lost their money through that. And I think that's what the general consensus is on the internet for the people that aren't part of the big companies that are pushing that tech.
And the trustworthy, did you cover that?
Well, the trustworthy comes from the lack of accuracy, so not having a knowledge base at the back end or even at the front end. So you put some text in, and the idea was that you could do your you could design your query in such a way that you're getting a good answer, but if you talk like a person, which is what the technology should ultimately do, I find pretty much 100% error rate on me just trying to naturally interact with an LLM and get the right answer. So that's my trustworthy
And the Alan Turing
limitation.
example. The Alan Turing example.
Well, oh yeah, the Alan Turing example's a horrendous hallucination when you consider that the output of things like that can be, people can use the technology, they can publish things on the internet straight from the LLM, that then gets caught up in the search engines, and then the search engines start pointing you to that page, and now you've got the wrong information being taught to the next generation that's using the tech, which is very bad.
Thank you. So let's just go on to one or two of the questions online. So linked to, I think the earlier question actually, but also combined with this, with some of the ideas from this last one. How do you recommend governments hold large corporations accountable for compromising sustainable targets? Do you have any ideas? I mean, I know, you have your ideas down south, in Australia. What do you think globally?
Look, I think at the moment we all have a voice, and the trouble is that you might not think you're being heard, but in the UK and in Australia, the governments and the people have been pretty strongly for sustainable industries. The airline industry is aiming for zero carbon emissions, carbon neutral by 2030 or something, or 2050. And that's like the most difficult industry to deal with. And now we've got the tech giants saying, don't worry about it, we're just going to keep doubling it every couple of months. And it'll be fine, don't worry, we've got, we'll pay taxes or something. And I think you just have to talk against it in order to be heard, lobby the local politicians. We did it to our local politician. She's organising a meeting with the minister in that area. And it's just such a strong case to say the technology is not ready for prime time. People are hoping it's going to be ready in a year or something. In fact, if you ask the CEO of one of these tech companies, they'll say, by the end of this year, we'll be replacing jobs. And they've been saying that for a while. It's not going to happen because the technology is not capable of that. So rather than the government sponsoring it, we should be talking to our politicians and saying, let's put a moratorium on it. Let's wait 2 years and see if it can actually replace people's jobs. And when it starts to replace jobs, then, okay, now you can start to talk about, well, how can we sustainably implement this?
Or even better, get excited by and help with more research in this new science. At the moment, all the oxygen is going to the large language models and generative AI. We can change that, and the people on this call can absolutely change the future and direct it in a way that have an influence over that future. Don't leave it all up to governments.
Yeah, and if anybody's got questions on your ideas of how to create sustainable AI, reach out after this. I'll provide the whole deck, because there were a couple of areas that you might want to read through. Ask some questions if you like, and we can just continue on, because I'm really passionate about getting the AI to work as much as the fact that you should be running it on your laptop or on your watch so that it's sustainable.
We'd love to hear from you.
Yeah, thank you. So not technology first, but people first is another way forward.
Yes.
Yes. And that collaboration.
Human-centered.
So over to another question to do with data. So data is gold. Absolutely gold. So this is one online. What are the most robust and/or emerging practices in the validation of data that is being used to train AI models? And they're particularly interested in fair and ethical representations, but in AI systems design.
Okay, well, in terms of the large language models, a lot of the content is outside of trusted sources. So Reddit, I think, and not Wikipedia, which is watched very closely, but things like Reddit content is just being absorbed at a massive rate, and so that's what trains the large language models, and a lot of the answers will be coming out of that. I think the secret is to, rather than doing LLMs where you're absorbing everything, build applications that simply have the content for the use case that you've got. So if you're a bank, have banking types of interactions set up, which means you need to understand language, which is what the rel and reference grammar system can do. But with a large language model, you start with a $100 million training run. It's got all of this stuff in it that you don't want in there, and then you have to try and work out how you protect the community from some of the opinions that are statistically being driven from it.
You can't control the data in the training data enough with the architecture of LLMs. Hence the need for a controllable trustworthy human-machine interface, which is what this new science is about.
Okay, I think that follows on to my last question, which was actually about how do you eliminate this training data and training cycles required by today's generative AI. So, so in terms of this alternative science, as you mentioned, can you just give us a couple of tips in terms of what difference that will make? Because yes, it's still, it's in its, let's not say it's in its infancy. There's been 2 decades and 3 decades of work on that. I can concur with that, being part of that. But it's not in its infancy, but it does need maturity.
Yes.
Can you give me a little bit more on as an alternative to this training, to eliminating the training data and training cycles by generative AI? So just some tips in terms of this alternative science.
So
That you're
in terms of
recommending.
in terms of the system that I
just to-
demonstrated,
so we can wind down.
there were a couple of principles, which
Yeah.
is I'm a computer scientist fundamentally, and what you do in computer science is you write your code and test it, and then you run your integration tests to ensure the whole system works. So what we're proposing for this is we follow the computer science techniques that have worked for the last 50, 60 years. We build a dictionary, we build tests to make sure the dictionary content is doing what we expect. We've done this already, and you can see that, like as a unit test, the language is working, the predicates are working as you would expect. Then you run it across other types of integration tests, like, let's load in this book, let's ask questions about the book, and the idea is to ask as many questions as you can possibly do, and because it's running on a computer, you can do millions and millions of tests very quickly. So the focus is on creating a dictionary for a language, and you do that once. Maybe we hit that. And you do that once. And then you keep using the language for the next 20, 30 years, making subtle changes to it until the language starts changing sufficiently that it doesn't work anymore. But the principle is you create the dictionary, encyclopedic knowledge, integration tests, unit tests, and just keep repeating. And then add other languages, because this technology should work so that you're converting any language into meaning and then using the meaning to run the world's applications.
Come build it with us.
Thank you. So just the last 1 or 2 questions.
I think there was a question.
Yeah.
Okay.
Yeah.
Thank you, John. Firstly, I have 2 questions before, but my senior classmate have already asked the first question on sustainability. And second one is, when you were speaking, you mentioned something, I might not get it verbatim, but you said that lots of people have ideas, but they don't know how to put in the work or something like that. So my question goes that, I found out that we students, when we are doing in our interaction, we have so many ideas.
Yes.
In between those ideas, we caught up with so many distractions. So what advice would you give us how to enhance those ideas? The solution to it?
So my suggestion is, when you come up with a good idea, you have to persevere with it. Talk to people. I've got patents on some of my work so that it's protected, because some of these things have taken 20 years to actually get prototypes working. But it's all about persistence and prioritizing it, because you have to make a decision: is this thing worth what you think it's worth in the marketplace? And if you've got a good idea that you can persist with, then you go down that path, and then you've got a lot of choices which people can help you with. Maybe you raise capital, maybe you sell your idea to a company that's working in that space. There's lots of choices at that point.
In our case, I would say very much networking. John had the science. We went, how do we do something with this? We know we need help. As he mentioned, we have to build dictionaries. We do it differently. We don't use training data. And we want to do it for the world's 6,000 languages. It's achievable, but it does need a community. It needs the global researchers. It needs cognitive scientists. It needs linguists. It needs coders. So in our own examples, I would say the position where we're at right now is that we are networking, we're getting the message out there. The book, they're just examples of what we've done. I extensively use LinkedIn, and I see professors like Kulvinder and in the UK, in Europe, in the US, starting more and more to use the LinkedIn environment or social networking, because that also connects you with industry and with other like-minded people.
Thank you.
Just examples.
Yeah, that's good.
So
So there was one question.
okay, go. Yeah. So there's one last question. Okay, thanks.
Yeah, so I know that currently like AI models are like improving themselves. For example, when a user enters a query, the LLM basically reevaluates it and responds to it more betterly. So I was wondering if there's any way that we can also, or is there any way that has been introduced, like that can improve the chain of thought? Like for example, the memory from the last conversation, AI mostly seems to forget that. So is there any way that we can improve that, or is there already been introduced, or what?
So people in the LLM community have asked me how could we improve things, and one of the answers would be validate what the questions are up front with this type of system. But in terms of the use of LLMs with the transformer architecture and the word vector architecture, I think there's loss in there that's very hard to get past. But having said that, I think the LLM industry's burned something like $100 billion in development to this point, and the robotics with driverless cars is also at about $100 billion. So if there's answers to those types of things, how can we improve this, then it's very valuable in the current world. As a scientist, I'm skeptical that we can make enough changes and make it cost effective, because you still ultimately, if you have to train a large language model and it costs $100 million, and you come up with, I'll just change this one thing, you're still potentially spending a lot of money just to validate it. But
that is a question. That's a research topic that Berlin University or HWR Berlin is looking at, with using our technology versus an LLM. Even with the limited dictionary that we have across a few languages, you can see what the machine's doing, what the language model is doing, whereas the LLMs are opaque. So that looking at how you can improve it, that is one of the research topics that's available, and we'd love to talk to people that are interested in looking at that.
Thank you.
Okay, thank you for that question. I think that was a really important question. That explainability aspect that you're referring to on LLMs and in terms of the science and using role and reference grammar, that's where the space, and that's where the two need some sort of comparison and fusion at one point, in order for us to move forward with the
Explainability and trustworthiness.
Exactly, these areas that are having ethical implications and issues of responsible future problems. So I think what we'll do is we'll stop there, and thank you so much those who came here to the room and those online. Sorry for the technical problems at the beginning. We were in a room which it was probably not ready for all the things we wanted to do today, but we finally got there in the end. We will share the slides with you as soon as we finish the actual meeting, and you'll receive that through your email. But thank you so much for joining, and if you have any questions, I'll be happy to pass them on to John and Beth as well. But thank you again.
And thank you, Kulvinder, for organising it.
Thank
It
you.
was a big job.
yes, thanks, Kulvinder.
Thank
Much
you.
appreciated.
Thank you. You're welcome. Thank you. We'll stop there. Thank you.